thermodynamics within and beyond general relativity, a promising link between gravity and entanglement.
Okay, thank you, Diptos, for the introduction, and generally we start by thanking the organizers, but here maybe the colloquium organizers, but nevertheless it's a great opportunity to get an audience where in a colloquium level we get to explain what we have, I along with my collaborators have been working on. So with that in mind, I have tried my best to keep it as non-technical as possible. That puts me at a risk of making things less rigorous, which I have tried not to fall in that trap, but please feel free to stop me at any point if you have any doubt or anything appears to be vague. I will try to the best of my capabilities to clear that. So we will be talking about black hole thermodynamics within and beyond general relativity, which is and also we will try to give a perspective on a promising link between gravity and quantum entanglement, or what we know as von Neumann entropy. So the color coding kind of decides the plan of my talk. So I'll start with a basic introduction to black hole thermodynamics in our well-known general relativity. Then I will try to go to the next part where I will discuss why and how we can go beyond general relativity and what can we say about black hole thermodynamics in such situations. And in the last part, depending on what time I have, we'll try to explain to you why this connection appears. So black holes are solutions in Einstein's theory of general relativity, which behave as thermodynamic objects. Now thermodynamic quantities like temperature, entropy, energy can be associated with certain geometric notions of the black holes just based on their geometric information. And these assigned thermodynamic notions, we will see, satisfy geometric relations which are analogous to thermodynamic laws, and we will term them as classical laws of black hole mechanics. Now I will come to it when I say I have been using this word geometric notions. So as I am saying it here, classical laws of black hole mechanics, they can be obtained purely based on the geometry of black holes, and then there will be a connection with the ordinary thermodynamic laws that we know. Now we also know that GR, or the general relativity, is not a complete theory of gravity. There are situations where this classical theory will fail. For example, when the universe started with a big bang, or we kind of go towards the singularity of a black hole behind the horizon, where the gravity is so strong that space-time curvature is huge, we cannot study the physics with classical general relativity. So we need a quantum theory of gravity, which is still not very well developed. There are certain candidates, but whatever be a proper quantum theory of gravity, when we take appropriate limits of it, by which I mean in a very vague sense, low energy limit, it will lead to what we know, the general relativity, and then it will add corrections on top of it. Now black holes will still be solutions even if we change the theory from general relativity to other theories beyond general relativity. Now if they behave as thermodynamic objects in general relativity, then it's expected that they should continue behave like thermodynamic objects even in theories of gravity which are beyond general relativity. The geometric identifications which I talked about, like attaching notions of temperature and entropy to the geometric objects of black holes, they might change as we will see, but the principles, for example the second law of thermodynamics or the zeroth law, will not change. We should expect that the black holes should, in a theory of gravity which is not Einstein gravity but something beyond that, they should still satisfy these thermodynamic laws, and they are not yet well understood. and this is where my research has been, I have been working on trying to understand and make some progress with my collaborators and students here in IIT, and I will love to talk about it in the second part. Now, finally, in recent times, there are lessons that one can obtain from quantum field theory and quantum information, which can be used to write down connections between entropy and geometry, which are very recently being unveiled. Now, what are those connections? For example, we will see matter entropy, normal matter entropy, be it a quantum entanglement entropy, in a region should be bounded from above by the area of its boundary. We will try to make it more precise when we say, but this kind of relations are kind of coming up, and researchers are trying to understand them, and people are trying to understand whether gravity is actually an emergent phenomena which kind of emerges out of quantum entanglement, and these kind of ideas are being floated. So we will see how is it connected with the topic, which is black hole thermodynamics. And when I say that there are lessons from quantum informations, there is something called relative entropy in quantum field theory or quantum information science, and it's known that this relative entropy is always positive, or it is monotonic. When it changes monotonically. Now, those are known results in quantum information theory. We will see how can we use them to say something about gravity. And they are at a very nascent stage, so they are not yet fully understood even in general relativity. So in the future, some of my research directions are focused on extending them, firstly understanding them in GR and then extending them beyond general relativity in those kind of theories which I mentioned. Now, this is typically an artist's impression of what a black hole should look like. You should see there should be some singularity which is predicted by the theory, which will be hidden behind a event horizon, and then there will be superheated gases which will kind of rotate around the black holes, and sometimes there will be kind of jets of relativistic matter which will come out from the axis of the black hole, and they will kind of they will evolve in a very high speed, and some matter, even if they are charged matter, if they rotate in such high speed, they will emit radiation, which we kind of hope to see. So this is an artist's impression, but this is an actual image. Probably some of you have at least seen this. This is an actual image of a black hole, which is so this is called a supermassive black hole, which is something around 4 million times bigger than the mass of the sun, and this is located in a distant galaxy which is known as M87, and the black hole which is here is known as M87 star. So in 2019, Event Horizon Telescope, which is an array of detectors, worldwide array of detectors which detect those radiations that come from the gas which is revolving, hot gas revolving the black hole, and from there they try to reconstruct an image like this. So in 2019 they first released this image of a black hole which is in a different galaxy, at the center of that galaxy, and in 2022 the same Event Horizon Telescope collaboration released a picture of a black hole which is there in our own galaxy Milky Way at the center of it, and these are kind of phenomenal advancement in science, and I say it's not just science, the engineering of reconstructing. So this is like hearing sound where all the notes are not available. We cannot have detectors everywhere placed. There are a network of a few, countably few, maybe 10 or 12 detectors all over the world. They try to see the data, which is the light, and from there they reconstruct this image. So the amount of engineering that goes in kind of simulating them and then checking which is actually the picture is tremendous. But for me, all I am just trying to see here, I am not an expert here, but in this particular topic, but what I am trying to convey is that black holes are real objects. So as a theoretician, I should have enough reason, or I should be able to convince you that they are real objects found in nature, and we should probably study and understand them.
Is there a scale to this image? Can there be a scale?
There are scale. For example, they know the resolution of the shadow of the core is 10 times less than the outside. This kind of, so this angle is something like some arc second. This is some cone we see in the sky, and it has gone to that resolution, some microsecond. I'm forgetting. I can show you the number. It's all there in that website. So yes, those numbers are definitely there. They have to give those things. They are all supermassive black holes. But one thing I must say, there is a leap of jump here, or a leap of faith here. We don't know yet convincingly, just as a proof that these are black holes. They might be compact stars as well, but it's generally expected that people can get so there was a Nobel Prize awarded in 2020 to Genzel and Zeng, who kind of previously tried to look at the motion of star which will bend nearby, and from there reconstruct this kind of an thing, not directly taking the image. There are overwhelmingly high support that these are black holes, because there are other properties. Compact stars cannot appear with that much amount of mass which they are predicting, but it's not yet really, one has not dotted the I's or crossed the T's that this is indeed a black hole. But astronomers and theoreticians believe that there should be a black hole at the center of our galaxy, and that's that. Okay, so then how do we mathematically describe black holes? The theory or the mathematical framework that we need is Einstein's general relativity, where the dynamics of gravity will be described by a curved space-time metric. This is going to be very important, and the matter stress energy tensor will act as the source of the curvature. This is exactly like Maxwell's equation, but the source currents, the rho and the j vector, acts like sources, and we go and solve for the electromagnetic potentials. So I'm talking about classical field theory. In electrodynamics, the classical field which we solve for is the gauge potential, or the scalar and the vector potential. Here, what I'm claiming is that the field variable is the metric. If I know the metric, I know how to calculate distances. In a sense, gravity is nothing but geometry as well. The matter, whatever matter it is, if it be a black hole, it curves the space-time around it, and all that we need to know is the curvature, which is the metric, the rule with which we will figure out the distance between 2 points in that curved space-time. And that metric g mu nu will come out as a solution to this equation. So Einstein wrote this equation in 1915, and as we have said, that black holes are solutions of Einstein's equations. So this guy, whose name is Karl Schwarzschild, he first wrote down a solution, an exact solution of this equation, meaning this is a differential equation. This is a second order differential equation, just like Maxwell's equations, on G. This R is the Ricci tensor, which is like the second, this is like x dot square or x double dot, the metric double derivative with respect to space and time. So this is a second order differential equations with boundary conditions. One should solve what these GAB are. Mathematically, these are 4x4 matrices, let's say. Now, a solution from this equation was first wrote down by Karl Schwarzschild immediately after Einstein came up with the theory, and that solution determines the gravitational field, or in a sense the metric outside the black hole. Now there is a story. So he was a German physicist, and when he wrote down this solution in 1915, he was serving German army in World War I. So in most of the time we kind of complain, we don't have this, we don't have that, and that's the reason we are not able to do things. So here is an example, a guy who was in World War I. In 1915, he wrote this solution, sent it to Einstein, and then he died in 1916 due to some skin disease which he developed immediately after the war. So the solution looks like this. I mean, we shouldn't get into the details of it, but this is exactly the rule with which you will decide what would be the distance between 2 points just outside the black hole. The black hole is spherically symmetric. The distance r, which appears here, is the radial distance away from the black hole. T is the time, and omega 2 is the metric on this 2 sphere, the theta and phi angle on this sphere. So with these 4 coordinates, I will be able to figure out anything that I need to know about this black hole which is sitting here. This black hole has a mass given by m here, and g appears to be the Newton's constant. Now, a particular thing about this solution is that this is not just, so I said this one should be able to map this problem with electricity and magnetism, electrodynamics. So maybe one is given a charge sitting here. I am figuring out the electric field and magnetic field outside. This is exactly that problem. The mass is sitting somewhere here, and I am figuring out the gravitational field outside, but it comes with a peculiarity, and which is going to be crucial in everything that I am going to say, is that r equals to twice gm, that distance away from the black hole, which might be thought of as the boundary here, appears as a event horizon. Now, event horizon is a location in space and time which decides the boundary between 2 sets of points or space-time points which cannot come with each other in causal contacts. Now, this can be understood from this picture very briefly. So this is the radial distance. This is something like time. So if you are outside the r equals to twice gm at this point, this is my light cone. So this is the outgoing light ray, and this is the ingoing light ray. Everything is fine. As you move closer to the horizon, and as you cross the horizon, you see the geometry decides that the light cone should be like this. So anything which should be emitted from here has no possibility of coming this way. It should always lie within this light cone. So this bending of light cone makes this r equals to twice gm as the one-way membrane. Anything can get in, but nothing can come out classically. These are known as some kind of a Kruskal diagram or Eddington-Finkelstein diagram. Now, why do black holes need to have entropy? Once that I have told you, there are geometries in black hole. There is an event horizon, and it was Jacob Bekenstein, his marvelous idea, which in 1972 he was asked by his supervisor, who was Wheeler, to solve this problem. What happens to the second law of black hole, second law of normal thermodynamics, normal matter thermodynamics, outside of a black hole, and assume that you are in a process where you take some information or some entropy, here is a cup of tea, and throw it inside the black hole. Now, black hole event horizon acts like a one-way membrane. We cannot receive anything classically coming out of the black hole. So is the second law getting violated? So whenever we are doing any experiment in lab and we see apparently there is a violation of a second law with normal matter and stuff, gas, ball of gas or dust, should we predict that there is a black hole? The guy has gone inside and we go home? No. So the idea was to kind of save, the only way to save the second law as viewed from the outside observer was to guess. It was a wild guess that the black hole should also have a entropy. So the outside guy losing some entropy means the black hole is gaining that entropy, and as a whole the total entropy increases. So what he described was that he called something like S generalized. So he assigned some S black hole, some entropy to the black hole, and then he added that with the entropy which was lying outside. And he claimed that there should not be any process where this change in this generalized entropy should decrease. That's what he proposed. And he not only assumed that the black holes should have an area, he could kind of give an idea or a measure of how much should it be. And it turned out that the black hole entropy should be proportional to the area of its event horizon. The area of its event horizon is like a sphere. If the radius, this RH equals to twice gm, which we discussed in the previous slide, so you take 4 pi RH square. That should be roughly the entropy of the black hole. Now, why proportional to the area? Because there were already some ideas which were there, how to make sense of this idea that black holes should have entropy, and moreover the entropy should be proportional to the area of the black hole. In classical general relativity, certain geometric quantities follow relations in close analogy with the thermodynamic laws. These results were already there, and these results, which I am going to explain to you, will give us, or this analogy will give us the fourth one we will not get into, but we will see the first three laws, how to understand that. So at that time there was this result by Hawking, which was there in 1971. He did some calculation in general relativity. He didn't care about taking a cup of tea and throwing it into a black hole. He was working with Einstein's equations and their solutions. So assume that there is a black hole of mass m1. So the area of the horizon will be 4 pi twice m whole square. I am putting g, the Newton constant, equal to 1 for convenience. The g is there. There are other constants as well. So this is the area of the first black hole. And let's say there is another black hole whose mass is m2. So the area of the horizon will be 4 pi event horizon of that black hole square. Now they merge and they form another black hole whose area is m3 square, proportional to m3 square, because m3 is the mass of the two initial black holes. Now the area law demands that the A3 should be greater than A1 plus A2, which it is obviously. So this is just a demonstration that I am giving you with a particular solution, but this kind of tells us the idea that if I forget about the comparison or the analogy between area and entropy, and if I just stick to area of a event horizon of a black hole, then the statement in general relativity, which I say are geometric relations, which says that the area theorem says that the area change in area will always be positive. Bekenstein knew this, and he argued that it should have some area. So he immediately proposed that the entropy of the black hole should be proportional to the area. Now similarly about the zeroth law, the statement of the zeroth law is that a system at equilibrium will have constant temperature all throughout. Now if I just forget about that statement now, and then I define something called the surface gravity kappa for a black hole, which is again a geometric quantity. Yes, please.
So you are assuming that black hole is a closed system, but those jets which come out, does it make it an open system?
So when you are thinking about the geometry side, this is just a demonstration that some black hole is at stationary, there is another black hole at stationary, suddenly they merge into each other and form another black hole, and I am showing that the area increases. But there is a theorem due to Hawking and Penrose, which is known as the area theorem, which tells that in general relativity you think of any situation involving black holes. There is some matter, jets are coming out. Actually those jets that you see are not coming from the black hole. They are the gas which are moving outside and they radiate. So there is, in a sense, you can ignore the black hole for the jet problem which you have in mind. But even you can ask me, what if I take a black hole and it's not a static black hole like Schwarzschild. It might be a rotating black hole. It might be a charged black hole. It might be a black hole which has a different topology of the horizon. Not a sphere, but a torus. They can have horizons. What happens to their dynamics? So there are abstract mathematical proofs as known as theorems in general relativity where this area theorem will work. So, I mean, ideally it should be an open system, so there should be some dissipation and all that stuff. Well, ideally one should approach those kind of a thing, but if you try to think of it as an open system, but the calculations start from geometry and it's not very well understood how to take care of those kind of effects. But if you just think from the geometry side, there is a theorem.
So event horizon assumes that nothing can
Classically.
come out of it.
Nothing can come out classically. I will come to it as I will discuss. There is something called Hawking radiation. I will just 2 slides later. So similarly one can define something called a zeroth law where the geometric quantity is this surface gravity. This is nothing but like the acceleration due to gravity near the surface of Earth. G equals to 9.8 meters square. As an analogous quantity for the black hole, an observer who is trying to stay afloat just outside the black hole must turn on a engine and must accelerate, otherwise he or she will eventually get into the black hole. So that kind of but this is a geometric quantity. Given the information of the black hole metric, I can compute it, and for the Schwarzschild metric it turns out to be this, and now this is a constant number. So over the event horizon this is constant. So this is a candidate for being temperature, and this law that this is constant over the horizon can be termed as the zeroth law, at least the geometric statement. And then there is a first law which says in a quasi-static process very close to the static black hole, if I start with a black hole with mass or equivalently energy m and area a, and then I change it to a new black hole with mass m plus dm and area a plus dA, one can start with this relation where area is proportional to the 4 pi RH square, and then RH is twice gm, hence area is proportional to m square. One can do a simple calculation, just have a differential d on it, it will be proportional to dm, then arrange some numbers here and there, and you get a relation like this with the definition of kappa which we saw in the last slide. Now if you look at this result and if you are tending to compare it with this result, then one should identify this quantity as being the temperature of the black hole. This area over 4g Newton should be the entropy, and energy should be mass. So that's how a geometric first law will work out. But you still want to kind of understand that this definition that T times ds was this quantity will equally work if I take kappa, if I add a C1 constant here and divide with a C1 constant here. So it was clear that temperature is going to be surface gravity, but entropy is going to be proportional to the area of the event horizon, but the proportionality constant was not known. And for that, an independent calculation of Hawking temperature was needed, and Hawking did that calculation. And that's what kind of this calculation where I will come back to his question. If something has an entropy, it must have some temperature, and then one should do a honest to goodness calculation to derive what the temperature is. And Hawking did an independent calculation where it requires intricate details of quantum field theory in curved spacetime. If you really know, there is something called Unruh effect where you have to choose the correct vacua. Even in special relativity, an uniformly accelerated observer will see a thermal radiation. An uniformly accelerated observer is like a gravitational system through equivalence principle. So we have got this hint that in quantum field theory, where you don't have a clear notion of time, your time and my time are different, so your vacuum and my vacuum are different. So if we choose that vacuum correctly, one can do a calculation where the gravity was taken classical. On top of that, we were doing a quantum field theory, but the field theory was quantum. That's why this is called a semi-classical calculation. And from that calculation, he obtained this, which kind of confirmed that what we were seeing as an analogy is actually not an analogy, and there is probably a further deeper meaning to this. And this kind of fixed the proportionality constants, and one should see that this is a very nice formula where all the constants, fundamental constants that appear in this formula. So yes.
So in the previous slide where you show that E equals to ds, right? So this is true for the reversible process, right?
Sorry.
So this is true for the reversible process.
Yes.
How do I relate this reversible process? What kind of reversible process you are talking about?
So I'm taking reversible process meaning. What have you in mind?
Let's say for A to A state to B state, or B state to A state, are the same.
So those are this kind Carnot engine kind of a setup, right? But here what I'm trying to say is this first law should be understood in a way where you have a kind of as I said here. So here this is called the stationary state version of the first law. So I have a solution space. In my solution space, each point are stationary black holes. I take two black holes which are nearby, and then there is a relation between them like this. This is not a physical process where I throw something into the black hole and I get something. So this is like a smart formula kind of a derivation of that. And there is another setup where you kind of take a object, throw it inside, let the black hole do whatever it wants to do and settle down, and then measure the parameters between them. That's called the physical process version of the first law. But what I'm saying here is just kind of I don't know in which process I go from this state through this state. The system have many, in the solution space, many points which all of them are stationary black holes. It has gone from one to the other very close by, and in that approximation this relation holds.
So then you equate geometrically, right?
I understand this relation geometrically, and then I compare this with this, and then I assign these values, or they have assigned these values. Okay, so far we have seen that the classical black hole mechanics in general relativity are kind of one-to-one correspondence with ordinary laws of thermodynamics, where a stationary black hole with Hawking temperature and Bekenstein entropy is kind of related to, is analogous, kind of same as a thermodynamic system in equilibrium with temperature and entropy. Now, as I was saying, I was giving you demonstrations. I took one particular black hole solution, which was a very simple Schwarzschild black hole, and I was justifying that this is true. But there are abstract mathematical proofs which were developed by Hawking, Penrose, and Bardeen and Carter, which justify that this analogy is probably more than this. Now, what more can we expect here so that we will believe it? One should have a microscopic understanding. Can I count the microstates of a black hole and match it with the area that is being projected from the geometry side? For that we need a quantum theory of gravity, and one of the candidate of a quantum theory of gravity is string theory. I mean, I don't work on them, but in string theory there are certain D-brane constructions which acts as a microstates, and if one counts them, they exactly match those area by 4g Newton. But again, they are not applicable to the black hole that we see at the center of our galaxy, because for control of calculation, these calculations can only be done on some idealized black holes, like some supersymmetric black holes in 5 dimensions and all. But in supersymmetric black holes in 5 dimensions, whatever idealized black holes they are, if you compute the area and then you compute the microstates and count them, the area over 4g Newton exactly matches. So that's kind of believed one of the success of string theory. Now, this was so far, yes.
It's interesting that the mechanism which can generate a black hole could be a collapse of a star, could be a primordial in nature due to some phase transition. Does it really show up in it?
No. Once you have a black hole, these results will work out. It doesn't really care about
How it
the
was generated.
was generated. So now the second part, where actually I will try to tell you about what I have been doing with my collaborators and students over here. So we will now go beyond general relativity. I have given you a motivation of why people should kind of think of going beyond general relativity, because that's not there are scales where strong curvature scales where general relativity will fail, and we should try to understand if we can extend these laws of thermodynamics for black holes to those situations. So that's exactly what I have been working on, and for that I use something called off-cell structure of classical equation motion following from arbitrary blah 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 blah. I will try to explain, but the details are not so important at this moment. And here are some references and some of my collaborators, and these are very, very importantly relying on a group of people who have been working on this topic. These are only recent ones. In last 6-7 years or a decade, this kind of work has come up. Now, why theories of gravity beyond GR? So I have kind of explained to you that black hole states are still solutions and should continue to behave as thermodynamic objects. So we should ask, does the law of black hole mechanics continue to hold in such theories beyond GR? Now, just to show you what kind of theories are we considering. So those of you who know if you ignore these two terms, this is the Ricci scalar and this is called the Einstein-Hilbert action, and this defines for me that this is Einstein's GR. And if I now add a matter part to it, which will allow my black hole to have charge, if I add a Maxwell sector here, I can have a charged black hole, and on top of that I can add any higher derivative terms. Now what do I mean by higher derivative terms? These are two derivatives of the metric, but I can prepare a bunch of terms like this involving the Ricci scalar, Riemann tensor, Ricci tensor, whatnot, and if you can count, for example, this term is a 2 derivative and 3 into 2 6, so 6 plus 2 plus 2 is a 10 derivative term, and this can keep on. So for this part I am saying that I can have any combination of these terms as long as they are diffeomorphism invariant. What is diffeomorphism invariant? I cannot just add a r mu nu rho sigma with free indices. I should add some scalar over here, some Lorentz scalar over here. With that conditions, this can be arbitrary higher derivative terms. Now, how to know that which term to add and which term to throw away? So if you have a quantum theory of gravity, which is a UV complete theory of gravity, then if you take a low energy limit of that, you get these kind of terms. At least in string theory you get this kind of terms, type 2 string theory on heterotic and blah blah blah. So there are enough motivations to consider this term, but I am not worrying about what the UV completion is. I will have any such possible terms here, and I will now test on the principle of second law on a black hole solution which I will derive from this, and that might act as a principle to decide which theory is good. If I take a theory for which I get a black hole solution for which I check the second law is not working, probably I can decide that theory is bad. In recent times people are working with these kind of things where they rely on unitarity or causality to decide what should be the low energy effective theory of gravity. Since we don't have yet a fully devised quantum theory, these kind of low energy principles, testing them on garden variety theories might be useful. So this is my setup. Yes.
So when you add those terms, so you use all the coefficients are also like alpha 1, alpha 2?
Well, the coefficients are dimension full coefficients, because if this guy has two derivative 1 over length square, this guy will have 1 over length 4, so this will be a length square type of a coefficient, and that coefficient will tell me at which scale this will be important compared to this. So they are dimension full numbers, and if you treat them as order 1 numbers like 10, 15, whatever, then you have less control, but you can also have them to be small.
And it is same for all the terms, or
That's what I'm saying. For me, I don't need them to be any specific. The result that I am going to say, you give me any theory, I don't need the particular form of the Lagrangian. The kind of result that I am going to say will work, but there are effective field theory of gravity where there will be an hierarchy. Hierarchy in the sense 2 derivative plus 4 derivative plus 6 derivative plus 8 derivative, and the coefficients will have similar hierarchy, so that there are length scales where the leading term, which is the 2 derivative gravity, is important, because that's where we live in. We should at least have a window where GR is a good theory. Then we will go to a length scale or an energy scale where the correction will be important. Maybe we are going close to the singularity of a black hole or going close to the Big Bang, and these terms will become important. So we can order it like this. So if I am a person from a quantum gravity perspective, then that should be the perspective. But if you talk to any gravity theorists, they say I don't care. Give me a Lagrangian, I will test it. Yes.
So, being a biologist, I have a question. So, GR is fulfilling the second law of thermodynamics.
Yes.
So, what is missing there? Why do you need corrections?
Oh, that's what I'm saying. GR is not a complete theory. We have situations where we need a quantum theory of gravity. And quantum theory of gravity is a theory of gravity which is way bigger than GR. Just like
So
we do
matter, you said matter. What is this matter?
a matter field, meaning normal matter. You can tell me that so matter meaning I have some quantum fields in mind, but just to give an example, I can have an electromagnetic sector. So my black hole will be charged under that electromagnetic fields. I can have a charged black hole. If I don't have this term, I have no way of getting my black hole to be charged. Yes?
So when you say that this checkpoint of velocity, you are just allowing those terms which are thermodynamically allowing the second one. Also some checks are from unitary this point of view. So are there terms which are at some intersection point of view?
Yes. So this is just for the experts. So there is something called Gauss-Bonnet law, and you can look at something called Shapiro time delay. Okay. So based on that, Kamano, Edelstein, Maldacena, and Zibydov kind of showed that you get a solution there, and there is a problem with causality. The time delay cannot be negative. Okay, it has to be always positive. So based on that, they say that those theories are not viable. Okay, but if you take a very small alpha, meaning those corrections are very small, there is a window where this can be a theory of gravity, and honestly speaking, no one understands. So what I am going to say you, I don't know, I am already close to the finishing. So I will be able to prove a second law in this kind of theories. I will be able to prove a kind of zeroth law in this kind of theories. Now you will ask me, then you are saying without depending on a particular model of theory. You give me any theory, I will be able, we have been able to construct a proof of second law in those theories. So then that contradicts with the requirement of causality as was put by them. No one understands why. That's an interesting direction. Okay, so these are other examples you can add. These F mu nu are electromagnetic field, they can couple with gravity, these are okay. Now in such high derivative theories of gravity, or most general theories of gravity, there is a definition, a geometric definition of black hole entropy, just like the area of the horizon, which is known as the world entropy. And it was derived by assuming or demanding that this satisfies first law. Okay, this was done around 92 or 94, that a definition, a geometric definition, which is not the area, but nevertheless it's a geometric definition. You give me the Lagrangian of the theory, I will make a differentiation with respect to Riemann tensor, and I will multiply with something called the binormals and evaluate it on the horizon. So these are just geometry data with which you can find a definition of an entropy which was given by world, which satisfies the first law. Yeah.
In the previous slide, if I can take you back, or the one before. So these higher derivative terms are should all be suppressed by Planck scale.
If you consider it to be an effective field theory, yeah.
How much modification in the matter sector would change your thermodynamic relations?
Acha. So for that, I will come to it. All that I need from that matter sector is some sensible energy conditions, that they have some positive energy and not. So these are classical proofs.
Okay, so any new degrees of freedom, for example?
So those will go into a more complicated direction where people don't know. They don't know. That was my third part, but most likely I won't be able to reach there. So there was a definition, but the information is that this definition it does not satisfy the second law. It does not satisfy the second law. So what we kind of did was we kind of proved the second law in this kind of theories, just to give you the overall idea. And how we did, these are not important. So what we considered was some stationary black hole. Let's say the kind of the physical picture that I have is, so the statement of the second law, black hole second law, is I start with a stationary black hole. Now a stationary black hole in GR has a technical definition that it has some Killing horizon. There is some Killing vector which becomes null somewhere, and there are rigidity theorems by people have worked out which says that every stationary black hole should have a Killing horizon. So I start with a stationary black hole and I throw some matter into it and I wait for some time, and the black hole does all the song and dance it wants to do, and then it settles down to another stationary black hole. And I want to compare whether the entropy has increased in this process. Now you can tell me that I am worried about the final entropy minus the initial entropy. That's what we kind of generally ask in normal thermodynamic system. But here what we have actually proved is a stronger version of that, which is in every time inside of this evolution the second law works. So what we have been able to prove is a local second law, which was previously only known as a global statement, that comparing this minus this. Now that needed something which for me is very interesting. So what we have achieved is that if you write down the action of any theory, or you give me a theory, I should be able to do the least action principle and obtain the equation of motion. The equation of motion in this case will be a tensor with two ranks or whatever. I am not getting into the details. What we have been able to do is to give a universal structure of this. You give me any theory of gravity near the black hole event horizon. If I evaluate the equation of motion near the black hole event horizon, or the more technically a Killing horizon, so this has a structure like this, and this has nothing to do with black hole second law or anything. It's like someone telling you that for Einstein gravity, my Einstein's equation should look like this, the off-cell structure of it. This is as general as this when I am not just working with Einstein gravity. So this is like a statement in general relativity, which we have actually proved along with student who has now graduated. Pratex was a key element in proving these results. Now using this and using some kind of a area theorem argument, this is some kind of an abstract calculation which I was telling you. There is an abstract proof. It's just not just two black holes merge and the final mass square is greater than the sum of the two mass squares. This is an abstract proof which tells us that this kind of a relation holds. Now I will tell you roughly what it means. This means that there is a del rho del t plus divergence of J kind of a relation which we see in electromagnetism. This JV and JI are the components of what we call an entropy current. JV component is the entropy density and the JI component. So if you have this picture in mind, this is time, this is away from the horizon, and this is the space direction on the horizon. So I started with one horizon at some time and I ended up with this horizon at some other time. People initially proved the second law by saying that the geometric quantity difference between them is positive. What we are trying to show is that in this evolution at each point there is a positivity of the entropy, black hole entropy and second law. And on top of that, what we are trying to say is that there is an entropy current on this horizon, and the fact that black hole is coming down to equilibrium cannot just be thought of by entropy production or entropy lost. On this slice, entropy can redistribute itself. There can be a spatial flow on that slice which is determined by this Ji. So in that sense, this is a local statement. So what we are trying to say is initially people were only talking about, in the original area theorem by Hawking and all, they were talking about del rho del T. They were missing this divergence of J piece, and in an entropy current we have been able to incorporate that. And so this is very interesting. One of the main input in this calculation has been what is known as Raychaudhuri equation, and this room is named by the same Amol Raychaudhuri. What he figured out was, let's say you look at the horizon surface and there are null directions or geodesics. Each of them are geodesics in which light ray will travel. Now if you have a bunch of them like here, this is the surface which is this surface. I am plotting it like this. So this is the V direction and this is the X direction. The X direction is this red line over here. So what happens is, if you take the small distance between two of this geodesic, this equation tells you how that evolves as you move in time. And you should be now connecting, if someone has a relation that tells you how this area is going to change as a function of V, that should be related to the area of the horizon and changing of that. And in that sense, Raychaudhuri equation was so powerful in deriving black hole laws. It was even powerful to help Roger Penrose get a Nobel Prize. The singularity theorem, that for which Roger Penrose obtained the Nobel Prize, the full calculation was relying on this equation. And in black hole thermodynamics also, when we are dealing with this geometry of whether this area is increasing or decreasing as a statement of second law, we are very heavily using this Raychaudhuri equation. So this is something I found. This is an article in Resonance, which is Indian Academy of Science journal. This is article by Sayan Kaur, wrote about Amol Raychaudhuri. You can see Raychaudhuri and two of the giants, Penrose and Hawking, relying on his shoulders. So this was very nice. While preparing for this talk, I found this. You can find this also, and there is a very lucid description of Amol Raychaudhuri there as well. So the first law and zeroth law for this kind of high derivative theories, we have also proved them. For that, we also had to look into the equation of motion of that theory. So we have been able to prove a linearized second law. So I didn't tell you, but our proof was not most general. What we have been able to do is that we take the stationary black hole, we perturb it, and we treat the perturbation to the linear order. We have not been able to go beyond the linear order, but there are people in Cambridge like Harvey Riel and all, they have taken our result and gone to higher orders in the perturbation theory as well, and then they are getting positive results even there. So a linearized version of the second law. The first law was automatic because world entropy was derived by making first law consistent, and the zeroth law was mentioned. Now in the last 5 minutes or 7 minutes, I will try to touch upon the last part, which this is more or less ongoing thing, where I will try to connect use this Bekenstein principle and the Bekenstein idea that black hole should have entropy, and how can we turn it into something which connects gravity and quantum entanglement. So we have seen that he derived something called this generalized entropy, where he added the black hole entropy and the entropy outside, and this is a geometric quantity and this is an information quantity. If you call this to be a quantum entanglement entropy or the von Neumann entropy, this is already a connection between gravity and entanglement, which you should note over here, and his statement was that this has to be positive. That's how this total entropy should increase. Now this total entropy should increase immediately tells you that, let's say I throw some matter into the black hole area will increase, and it has to increase by an amount which the matter entropy had fallen in. So the black hole should know, so the classical GR should know about the quantum states of the, okay, I wanted to mean this line, I don't know why I wrote this. So the black hole should know about the matter quantum states. If it doesn't know, then this limit, I can just kind of, I can just take this limit that this S general is positive, which is the change in area plus change in S out greater than equal to positive, into some kind of a bound which is this. Now this bound can be thought of on the matter entropy as well. So the matter entropy that has fallen in, which is this delta S out, should be less than the area change of the black hole. Now Bekenstein used that and came up with this formula. He used some thought experiment of some ball of gas, throw it into the black hole, such that the energy change is optimum, so that you can challenge this bound. If you change of area is, if the change of area is minimum, then you can asking how much is the upper bound of storing matter entanglement entropy within that matter system. So if you view it in that way, this bound kind of gives you a connection between geometry and entanglement, which was first wrote in 1981, but it was later kind of proven rigorously by using theorems of quantum field theory, where this change in entropy was related to something called the modular Hamiltonian, which was like the density matrix of a system, and you compute the entanglement entropy, and from there you can use this fact that there is something called this relative entropy, which is the difference between a quantum state rho and a quantum state sigma. Let's take sigma to be your vacuum state, and rho is some excited state in a matter system. There is no gravity so far. This is just quantum information or quantum field theory. Now this quantity distinguishes the state rho, which can be a slightly excited state, with the vacuum state, and it's known in quantum information that this relative entropy is always positive. Now if this relation from there immediately follows, which is a more rigorous formulation of the Bekenstein bound. The Bekenstein bound, you might think like a hand wavy kind of thing, thought experiments and all, and it was a rigorous proof in a theory without gravity, where people have been able to get this kind of a theory. Now what we have been able to do was to take a version of this bound, which is also known as the holographic entropy bound or the spherical entropy bound. I'll be not getting into these details, and the statement of the bound is like this. So let's say you take so these are space directions. This is my region in space, let's say some space on the top of this table, and I chose a direction which is a boundary. I contain the region within a boundary. So there should be a measure of how much entropy one can contain in that region. And what people have said, that you should not be thinking like how much entropy is contained in that spatial region, but what you do is shine light rays from that line. So this link is time. So if you shine light rays, this ring of sphere, a circle, will come to a smaller ring or a greater ring. Now, you see, this thing eventually encompasses the matter that is within here. And a matter can kind of, if you draw its future light cone, it will cross this surface. So there is a flux of this matter entropy across this surface. Now you ask the question that what is the matter that can cross this light surface, this light-like surface, and one can rigorously prove in general relativity, I am not getting into the details, that this SL is the amount of normal matter entropy that can pass through this light sheet. These are light rays and this is a light sheet. How much matter entropy, flux of matter entropy can pass through this surface will be bounded from above by the area. In this case, this is just length of this initial line circle and minus this one. Okay, this can also be rigorously proved as I shown using properties of quantum field theory, but here you are kind of restricting matter entropy, which is some von Neumann entropy or one-term entanglement entropy, using geometries. And the genesis of this bound is the kind of thing that I was telling you, and we have been able to generalize that to arbitrary theories of gravity. So where there is no support of quantum field theory derivation, but this classical result that we have been able to prove using classical laws of black hole thermodynamics and geometry, we expect that this kind of a relation should hold even in high derivative theories of gravity. Doing a quantum field theory for those kind of high derivative theories is very challenging. It's not yet been developed, the formalism. People are studying it nowadays using something called algebraic quantum field theory, algebra of operators and stuff like that, which might be useful. So what we have been able to do is to generalize this, where this area naturally, as expected, should be changed by world entropy. Since we are considering higher derivative theories of gravity, the natural definition of entropy associated with a surface, not just black hole horizon, should be world entropy, and there's that kind of a bound exists in all such arbitrary higher derivative theories of gravity. And there is some modern quantum version of it, which Shobho was probably asking. People are looking at something called quantum focusing conjecture, which relies on the result of Raychaudhuri equation, which is a classical focusing, and from there people are trying to derive this in high derivative, in general relativity first, and then probably our result holds true, we can get this kind of relations. But yeah, so I'll leave it there. Yes?
So then for the Hawking entropy, we have the entropy as directly proportional to the area of the event for us. Right?
Yes.
But my question is that the way we calculate the area, is that a diffeomorphism invariant quantity or not? Like, is it different in different coordinate space?
Well, if you give me a ball and you want me to calculate the surface area of it, if I change my coordinates, the area should be same, right?
But in GR there is this notion of invariant volume and invariant area.
So you kind of do this kind of a situation, right? If you are computing, let's say volume, area is area of a 2D surface, a volume is this, right? So as you know very well, this is, I don't know, this is a covariant quantity. So yes, the answer to your question is yes.
This is the volume. Now for the area.
Well, area you kind of do rate is the induced metric on this line. Well, d2x or d1x, if you want to find this area, just compute this with appropriate boundary and you Okay, so the thing is, to answer all these questions, I should need a proper setup of quantum gravity. Now, what happens in string theory, if you take that to be a quantum theory of gravity, there are two parameters known as the alpha prime, which is the string tension, and the other is the G string. Now, G string decides whether it's your quantumness, and alpha prime decides, well, you have had derivative corrections, but the G string is still going to 0. So you kind of go in higher orders in alpha prime, but keep the G string to 0. That's why the real stringy effect or the real quantum gravity effects are not important, but you can add with your Einstein gravity some corrections and treat that whole thing classically. Now, these things are motivated by this alpha prime corrections in string theory, but the fact that I am at Gs equals to 0 will still allow me to do a classical gravity. It's just that the action has changed.
And does there exist any observational evidence for?
Well, people try to kind of relate it to, let's say, dark matter or dark energy in cosmology, and then try to, but they are like, so you are asking me if string theory has any observational significance. There are bounds people have computed, but they are beyond the resolution of the present day experiments.
One attended question.
Yes?
These calculations critically depend on the existence of event horizon normally, right?
A killing horizon, to be very specific.
Killing horizon yeah. So, like, but such a thermodynamics in general should exist very far from the event horizon or killing horizon as well. For example, the Undu effect would exist in any, like, regardless of the crystal, right? So, the respective thermodynamics in the crystal should exist there as well. So, what do we know about it?
You know, wherever you want to have some thermodynamics effect with gravity, there should be a horizon. If you know, the Unruh effect is like, this is the uniformly accelerated observer. That comes with a horizon, which is a Rindler horizon. That Rindler horizon kinds of doesn't allow this region of space to be in touch with this. And entropy is a common concept where you don't have a full information and you kind of do a tracing out of this part. You have a box with microstates, you don't know. So you zoom out and assign the lack of information. So in gravity, similarly, whenever you have, so I had no horizon, I had no black holes here, but a horizon was there, and all that I am trying to do here will apply even there. All these thermodynamic effects will apply to cosmological horizons. We know we live in de Sitter space and there are horizons. So whenever you have a horizon and it turns out to be a stationary or killing horizon, to be very technically correct, all this method will apply,
So,
even in high derivative theory.
I guess the other way to ask would be for thermodynamics somewhat away from the event. Like, for example, the calculations were mainly near the killing horizon, right?
Near the killing horizon, yes.
In the approximation of near the killing horizon, if you actually consider the situation far from the killing horizon, is there a formulation between?
Well, you have to come up with the formulation, then I will see. Here I had a specific physical situation where I was throwing something in the black hole and the black hole was growing in size, whether the total thing was obeying second law. So you come up with a situation where far from horizon you have a thermodynamic setup. What do you mean by thermodynamics? Far from black hole, I don't know, there are quantum field theory, and quantum field theory you can do thermodynamics or statistical field theory. But are you interested in gravity effects? Then you probably have a situation far from horizon where gravitons are present. Then can you do something where you need a quantum theory of gravity? These are all, hard for me to explain or answer right now. If you give me a particular, what I am saying is very certain. If you have a killing horizon of any kind, like the Rindler horizon in special relativity, cosmological horizon, Here I was talking about an event horizon or a real black hole. All the setup that I was discussing will apply. In all those setup, this is a certain situation. Now, what you were suggesting a bit, for me a bit, I don't know, I need to speculate, and if you give me a concrete idea, I can comment.
Okay, thank you. Let's thank Nilay once again.